We shall continue our discussion on basic file systems. We have discussed in the previous class that how data is stored in a disk, because we are mainly concerned with storing data in a disk because it is a direct access device, and how data is stored in tracks in which we have blocks, and in each block we have some records, and these records are organized into what we logically call files. And today we shall discuss in more details, though not in the fullest sense of it, the organization of files. So the topic of today's lecture is file organization. File organization, that is how the records will be organized in files. We know how once it is organized, how the records are going to be placed in blocks, and how blocks are stored on tracks, and how tracks exist on a disk, and how a disk is accessed depending on its track number, block number, and then record number. We also know that the disk accesses data block by block, in the sense that when it reads or writes, it reads one complete block or writes one complete block. It does not individually read or write records. We have to manipulate complete blocks. That is a very important criteria to which will decide some of our data structuring techniques here. There are various types of file organizations. The first is called a heap file or a pile. Then we have sequential files, index sequential files, hashed files, B plus trees, etc. So we shall first discuss them one by one. The heap file or pile is the simplest form of file organization, in which data is just piled up or stacked up one after another. For example, if one record comes now, so it is going to be stored conceptually in the end of the file or the beginning of the file. When another data comes, it will be stored here. When the third data comes, it will be stored here. Searching means you start from the top or the bottom, any one place, and you scan them one after another. So when records are there in a file or in a heap file, then they are just stacked one on top of the other. So the idea of heap file is insertion is done by stacking. Deletion is done by setting a field in record that means that if you want to delete a particular record, this record is not physically removed. What is done is you have an additional field. So each record is extended with an additional field, which denotes that whether it is deleted or it's available. If it is still deleted, then it is marked 1 and available is marked 0. So this field denotes whether that record is deleted. Physically nothing is done. And search by brute force. It is a brute force search from the beginning or from the end. Just scan them one by one. Neither are these records sorted. They are just placed as and when they arise. And you can have an additional garbage collection mechanism which from time to time reorganizes the file. What do we mean reorganizes the file? Just removes those which are deleted and maintains the rest in its original order. This heap file or pile does not have much advantage in most situations, because it really does not help in the search. Insertion is very easy. Deletion means find out and search. search and delete. So whereas insertion is very easy, the rest of the operations are very expensive. And if you have something in which you are merely going to insert data and very few times you are going to search or delete data, then you may use a heap file or pile. But this is not a normal case unless it is just a data entry operation. You may just put into a heap file and then later on you may process it and convert it to a different type of a file. It's only when you have got a lot of data entry to do, you may use a heap file. This is not very important in most database applications where searching is a core operation. The next are the sequential files. In a sequential file, records are kept in sequential order on some attributes, and this is usually the primary key. That is, if you are given a set of records, then they are kept in strict sequential order according to their primary key value. So the records are there one after another, and the sequence is strictly according to primary key value. This is the idea behind a sequential file, so that whenever you have to scan or do something on all the operations, you can scan it based on the primary key value and then go one after another, and searching will take you through the primary key value and you will reach that particular record. Let us consider this example where we have got accession number, title and year of publication. And suppose at this point of time we have got it sorted according to this accession number key. These are the books and these are the year of publication of the books. This is how suppose they are stored. Now let us see what we will have to do for insertion, what we will do for deletion. So we have got three major operators: insert, delete and search. Search or find. Now the first problem comes up. Suppose we want to insert a book. Suppose we want to insert this record. Now this record will logically come here. After 5732, we have 5733 and then 5734. Now in order to do this insertion, we may have to, if we want to maintain this strict order, we may have to push all of them down and insert this in this particular place. That is one option which we may have for insertion, but that is a very expensive option. It's expensive because we have to shift all these records, and the number of block accesses, suppose there are 3 records per block, then you can well imagine that in worst case or in the on the average case, the half the number of blocks may have to be shifted up and down at every insertion step. Similarly, after deletion, if we shift everything up, then the same problem is there. Searching is fairly simple. We just start from the beginning or the end and scan them one after another. But it is to be remembered that this searching is a block search operation. And when you have to search, you don't search record by record. What you will do in a sequential file search algorithm, you will first get a particular block. Search is a block search. You will get a block which may be 3 or 4 records or even 10 or even 20 records, and then on that block you will have to search these elements. Now this block will be read from the disk and may be stored into a table array which has got the same structure, and in that array, because these are sorted, in that array you can do a binary search. So this block search is actually a mixed binary with sequential search, in the sense that it gets a block and does a binary search in the block. If the record is found, you stop, otherwise you continue. This is the basic principle of. This is how it is slightly different. If it was a sequential linked list, say a sequential file in a normal operating system environment where we write a program, we would have accessed it record by record. But here we will access it, since we will access it block by block, in one block we can do binary search. So get a block and perform binary search on that block. This is what we will do for a search operation. But the basic naive insert and delete operations will require shifting, that is, will require pushing them up and down, and that is quite a tedious task. So we have to find out a simple structuring mechanism by which we can modify this and make it simpler. We will use the same ideas which we use in pointer manipulation, and we will develop the ideas slowly. What we will have is, other than the attributes, we have got the accession number, we have got the title, and we have got the year of publication. Other than this, we will maintain another one called the next. This next will tell us which is the next sequential block, which is the next sequential element in the block. For example, in our situation, it was we had this book, we had 5732 database, we had 5734 another database, we had 5735 algorithms, and we had 5740 graphics. The next pointer list will be like this. So this tells which is the next record in the sequence. Now suppose we have to insert a new record, as we said 5733, then we will insert it like this: 5733 graph theory, graphs, let us say. This book was 1994. and we will manipulate the pointers. We will now remove this pointer, we will make it point here, and we will make this point here. So, we will remove this. Now, the sequential axis will be along these pointer links. This is how we will maintain the axis. The difficulty here, this idea is fine, but the difficulty of, so insertion is easy, we do not have to push all the blocks up and down, but it makes search slightly more inconvenient, because now when you access, suppose these 4 form a block. Now, when you access this block, then in order to, you cannot now perform a binary search so easily as you did previously. In order to access this, you will have to get another block, and in that block maybe you will find this. So, the advantage of binary search which we had in a strict sequential file will be slightly lost if we maintain this, but then we will have more advantage in insertion and deletion, and that advantage is drastically better than what we have now. So, wherever we insert, we will continuously insert like this. Now, deletion. Suppose we have to delete this one, then this pointer will move to the next one. This one was pointing like this. So, this pointer will be removed. So, we will have to delete this one. So, suppose we delete this one. In order to delete this, this pointer will now point here, and this pointer will be removed. This pointer will point here, and this pointer will be removed. So, I will redraw the pointers now, as it will now look. This pointer will be like this pointer will be like this will point to this place, and this one will point here. So, the next pointers will be like this will point here, this will point here, and this will point here. So, the more and more insertion operations and deletion operations are performed, this structure will become more and more non-sequential in the physical sense. Logically, we are maintaining pointers to have the sequential property, but physically when you lose sequentiality, what will happen is the number of block accesses will increase in the case of a search. So, in every such file system, you will have the concept of reorganization, which will from time to time, see at the end of the day when nothing happens on the file, nobody is working on these files, no insertion or deletion operation will go on. It will rearrange the whole file, so that it is now again in strict physical sequential order. So that when you start the next operation, next day's operation, you have got a file which is strictly sequential order. There is another point here. Suppose I delete so many, like I have deleted this one, then I delete this, then I delete this, then I insert 3 and I want to insert another one. I would definitely, if I do not utilize these places which are deleted, and my file will be misutilizing space. So, other than that, other than these insertion, I must be able to insert not only in the free area, but in the area where deletion has also taken place. These are simple data structuring techniques. So, how will we do that is the next question. This is the organization that we had. I am not writing out all the fields, so that this is deleted. So, this points here and this is grounded. This was the situation which we had. This points here, this points here, this is here, this is here, and this is grounded. Along with this, and obviously we will have a pointer to the start of the record. This is the start. This is the start, because even this could have been deleted, therefore the start would have to be modified. Suppose this was deleted, then the start would be modified, because this is not the starting element of the file. Now additionally, we will have another pointer structure using these next pointers only, which we call the available list. The available list will point like this, like this, and this. This is the available list. This is the green colored ones will point to the free records. This will point to the free records. Now, whenever I insert an element, I will go to the first record in the available list and put it there. I will go to the first element in the available list and just put it there, and the new available pointer will point to the next one, and this will point to the sequential element which we need to point next. I will show this in a simplified structural diagram later. Let us forget the other fields and let us have only one field. Initially, this is the structure at the beginning of the day, let us say. I am drawing the available ones as another pointer, but this area can itself be used for the available pointers. In order to understand it better, I am just using another set of pointers. But actually they are the same ones, so that the drawing is more clear. This is how we have it in the beginning. Now suppose I want to insert a new record. So I will find where I want to insert it. To find that, I will start from the beginning. And suppose I want to insert 5, 7, 2, 3. Insert. At this point, I will come here. This is 5, 7, 2, 2. This is 2, 4. So 2, 3 will be inserted after this. I will go to the first available slot using this available pointer. So I know this slot, and I will make this one point here, this one point to the next one of this one. So I will change this pointer. This is the pointer which I will change. I will remove this, make it point here. This one points here, and the available pointer now points here. Mind you, this and this are the same one. So this one now actually is this one. So we have got this available list. Now at this point of time, I'll just redraw it, because since we cannot erase, I'll redraw it so that we can understand deletion better. Otherwise the diagram gets very cumbersome. Here actually we have inserted 5723 here at this point. The pointer structure after insertion now looks like this. This is what it looks like now. And suppose I have this is the operation which I have. So what will I do? I will first find it out, search it out sequentially, and I have searched it out here. So my steps are, this will now point to the next one. So 5721 will point to where 5722 is going to point, was pointing to. 5722 was pointing here, so this pointer will now point here. This one will point here. So we have physically removed this, and in order to reutilize this space, this pointer does not exist now, and this will be made available, and I can either make this point here and ground this, or I can make this point here and this point here. So let us take any one of the conventions. What we will do is, we will now make available point here, and this will point to the one where available was pointing to. So next time when you want to insert anywhere, you will insert it here. So you reutilize the space as much as possible. So at this point in time, our insertion algorithm is get the block, our insertion algorithm, the first thing we have to do is have the find or the search algorithm. Search. The search will now not be a pure binary search algorithm. It will get the block and then move along these pointers. It will move along these pointers, and once it moves along these pointers, it may have to get an element from another block. Without scanning the full thing, it may have to get an element from another block and start scanning there. And then after some sequence of scanning, it will locate where it has to be inserted, or where it has found the record or not. Now after find, we will use this find or search for insertion as well as deletion. For deletion, we will search it. If it is not there, it's done. If it is there, then the previous and the next pointer. During the search, we will keep track of the previous pointer. While finding an element, we will not only have the element, but the previous element as well. And we will make the previous point to where the element was pointing to. We will free this place by making the available pointer point here, and this will point to where the available pointer was pointing to. So these two are actually the same location, it will be used for the available slots where it is free, and it will be used for the next pointer slot where it is given. Now, there are various strategies to improve on this scheme. We will not elaborate on them in details, but I will give you some ideas of what these strategies are. The first strategy is obviously reorganization. From time to time you reorganize it and make it strictly sequential, so that your search does as few block accesses as possible, because more and more insertion and deletions will start making this for every record you may have to access one block, and it will be just like what a pile was, searching beginning and end, just here and there you will search. The second is that you organize it in such a way, because you know that you are going to get block by block. So, you organize it in such a way that when you have to insert it, you try and insert it in a block which is related to that record. The idea is this: you have got blocks. Suppose a block can store some 20 records. So, you will have a block pointer which points to the next block in the sequential file. And for each block, you will have some slots like you had here, the next pointers and the available ones. So, you have the next pointers and you also have the available pointers. That is, for the block you have the next, these are filled. And these are two are free. Here also you will have some filled and some free. So, this one will go to the end of the block. 5721 will point to 5724, that will point to 5726, and this will point to end of block, and this will point to next block. Similarly, here you will have next block, and suppose this is free, this will point to end of block. So, you have left some free space. What is the use of doing this? The use is you try to insert in the free area of the same block. You try to insert in the free area of the same block. If you cannot insert in the free area of the same block, then you define a new block, make this point next here, this point. The advantage of doing this is that even if they are not in sequential order, it is expected that they are in the same block or in a block which is relatively close. They are packed together as close to each other as possible. And then you can reorganize the blocks. From time to time, when you reorganize the blocks, you redo the whole thing. For every block, you leave some 10-20% free and reorganize the blocks. So that insertion is done not at the fag end of the file or at an arbitrary place, but in a block which is close to it. So, this is the organization of a sequential file, and all such organizations which we will discuss, in many of them, this sequential file component will always be maintained. That is, over and above this sequential file, we will have several other structures which are accessing it. But the sequential file, that is, why is the sequential file important? Because we will often access it along the primary key, and we may access all the records according to the primary key. Since this operation is very frequent, this sequential file accessing through blocks is often used as the criteria for designing a sequential file. Next, we come to in a sequential file, the problem with a sequential file is that access is sequential. Whenever you have to access anything, access is directly from the beginning to the end. Whereas disk is a direct access device, and if we make sequential access like this, then we will lose lot of advantages. The conception of an array in normal programming is the pure direct access concept. We give the array index and we access that element out of that array. How much of that idea we can expect out of a file system? That is the next topic. So what can be suggested is, you have got a sequential file. Over and above this sequential file, you maintain an index over the sequential file. What is the index? The index is a smaller file. The index is a smaller file which is sorted according to, say, one of the keys, say primary key. Let us take an example. Let this be the sequential file. It has got all the next and available pointers. I am not drawing them. Five seven two one, 5722, 5724, 5726, 5728, and here we will maintain some of the accession numbers. 5721, 5728, 5740, maybe this one starts with 5740, 5748, so here we will maintain some of the primary key values in sorted order. This is the index file. This is another file. This is another file which has got the primary key only. The record structure of this file is a primary key and a pointer to another record. And this is sorted. This may contain all the elements of the key or only some of the elements of the key. So this says 5721 starts from here, 5728 starts from here, 5740 starts from here, 5748 starts from here, and 5790 starts from here. Now, suppose I want to access an element 5746. In a sequential file, I would have started like this and accessed it. Here, I will look at the index file, and in the index file I will come here 4048. So I will go to 40 and do a sequential search from 40. I will do a sequential search from 40 to see whether I have 46 or not. Now this, if this index file will be another, these elements of the index file will be another sequential file. The elements of this index file will be another sequential file. And you will do a block access. Suppose this is one block. Suppose this is one block. Then you will just access one block, scan it quickly, and get the pointer and access the actual file. The index file is expected to be much smaller than the original file, but it is also expected to evenly break up the sequential file, so that your access becomes much reduced. Access time is reduced to a greater extent. Now this indexing may be what is called a dense index. A dense index means all the elements which are here of this index may be done by a primary key, by even a part of the primary key. Suppose a primary key has got 3 attributes, you may do it on two of the attributes of the primary key, because if you do it on all the full primary key, you can be sure that each of them is corresponding to only one record, because if it's a primary key and you do not keep duplicates, then each of them is going to correspond to only one record. So in a dense index, you keep all the keys on which the indexing is done, all the attributes, the values of all the attributes on which the indexing is done. This is not a dense index. If it were a dense index, I would have had to have all the values. For example, suppose in a bank, account number and the customer name, because you can have joint accounts, therefore account number and the customer name together forms the primary index. Then you can have an index on the account number alone, dense index on the account number alone. You can have a dense index on the customer name also. But whatever index you have here, the file must be organized according to that key, at least that key or part of that key. That is what is the idea. It is organized sequentially according to this. Therefore, here we have got the attribute here. What we have here is what is called a sparse index, in the sense that all the attributes, all the values of all the attributes on which the indexing is done is not present here. So in order to increase our accessing, we have put in another file which is called the index file, and we will first search this file and get the appropriate pointer and then search the sequential file. So that is why it is called an indexed sequential file. But if you have noticed till now, in a pile we inserted very simply and searched the whole thing. In a sequential file, we tried to improve searching a little and made our insertion and deletion more complex. So here we have tried to improve searching more, but our insertion and deletion will become more complex. For example, if we insert a new record, then if it is a dense index, we have to update this index file as well. If we delete a record on a dense index, we have to update the index file as well, because we will have to delete the attribute corresponding to the key where this value existed. That will have to be removed, and that removal on a file like this is similar to the removal on a sequential file, as we have discussed earlier. And if you want to insert or delete, you will also have to modify the index file appropriately. So this is a sequential file, this is a sequential file, and they point out like a dictionary to help you access the chapters as easily as possible. Deletion, if you delete this in a dense index, you will have to delete this. In a sparse index, if you delete this, this need not be deleted. But in a sparse index, when you suppose I delete 5748, then when this 5748 is deleted, I may have to replace it by 5749, or I may replace it by 5749 and put it here. If it is a sparse index, if I want to utilize the indexing space, then instead of just deleting, I may replace it by another one. The advantage of this index sequential file is it gives you a faster access. But due to a large number of insertions and deletions which can really happen, the index file itself may become topsy-turvy. This may not be sequential because of a lot of insertions and deletions, and the file here may not be balanced, because this may point to some 20 records, Previously when we did the original indexing, when we took the sequential file and indexed it, then we made sure in a sparse indexing, say, we made sure that all of them are equally distributed. If there are maybe 20 elements to each of them. But after a lot of insertion and deletion, this may become skewed. And this may become skewed, some points to a huge set of elements and some point to only a few set of elements. So at this point, a lot of reorganization may again be required from time to time. So index sequential file may require reorganization also from time to time to maintain not only the sequential file, but also to maintain an index file which points to equally distributed number of elements in the sequential file. Moreover, once we have had the flavor of indexing, let us look at this example. We have got an index file which may consist of, say, 3 blocks. This is the index file. It consists of 3 blocks. And this is our original file consisting of several blocks. This was the structure of the index file, and this is the structure of the sequential file. This points here, this points here, this points here, this points here. This is the way we may have organized it. Now, in order to access an element, I will have to go from the beginning here. If it is a dense indexing, it is fine, I have got all the elements. The idea is, why don't we index the index file? Instead of searching this whole thing, because the index file may be a huge file itself, why don't we index the index file? It may be a dense index here, we have a smaller sparse index to index the index file. Or both of them may be sparse, and we have what is called in general, what is called a multi-level sparse indexing. This is the first level index file. This is the second level index file. And this is finally the data files, the sequential data file. So in the first level you get here, and then you point here, and then you come here and you get the actual element. And you can have more than one levels, but as I have mentioned earlier, the cost of having a better insertion, a better search through this will tell upon the insertion and deletion mechanisms. Once you have a multi-level indexing scheme, when you insert a new element, you have to update all the levels of indices. When you delete, you have to update all the levels of indices. The algorithms are not difficult, but 2 or 3 things have to be kept in mind when you design these algorithms. Firstly, whereas this looks like a file here, these are actually a set of blocks. And when you have a multi-level indexing scheme, you would prefer that this is just one block. This is one block. This is one block. So all of them now are just blocks. This points here in the sequential file. As we discussed the block pointers, these are blocks, and you will have something like this also. And this is the first level block. So you can have a multi-level scheme in which these are all blocks and this points to the reorganization, 2 level, 3 level, 4 level. What is the optimum level is the next question. And how will you reorganize, how will you redistribute so that everything is done in a proper manner. This is a question which we will answer when we discuss what are called B plus trees. How to do them? How to have a dynamic number of levels. The B plus trees are structures which maintain a dynamic number of levels. The number of levels are dynamic and the distribution is such that they are all always equally distributed. That we will come to later on. But in many cases you have got a single level or 2 level fixed indexing schemes also. Till now, whatever we have discussed are indexing related to the primary key or subset of the primary key or part of the primary key. Suppose we have to index onto, what is the advantage of indexing? The advantage of indexing is that select from this where B0 name equal to Vijay. That means you have to quickly go through that key and find that name. Now we may have a lot of queries in which we access something which is not a primary attribute, maybe addresses. So in that case maybe it is efficient to have indexing on a secondary key as well. So how will we do indexing on a secondary key? Remember, the file is physically organized, the data file is physically organized in the primary key. Though I am drawing it like this, these are blocks. So let us do it in a blockwise fashion. These are blocks and you have got your next pointers like this, the block pointers like this. They are not organized according to the sequential file is always done according to a primary key. Now I want an indexing on a secondary key. How will I index it on a secondary key? Suppose, let us take an example. I want to index it on title of the book. The book is organized, these are all organized according to the accession numbers, and I want to access it based on book title. A sparse indexing on book title. But here it is organized, the sequential file is organized on accession number. So these pointers are pointing to by accession number. So I may point to the first record in algebra, but the next record here will not be the next related with A or algebra or something like that. So I can have another set of pointers which point to the next one here or the next one and then this one. So I can have another pointer, the next pointer corresponding to this attribute. That is, I may have a sequential file organized according to one key and I may have an additional list of pointers according to another key. This is one idea which I may put. I may have this one pointing, then this one pointing here, then this one pointing here, and so on. And this will point to the actual record somewhere like this. And I will use another set of pointers to move up and down. But remember that when if I have to move sequentially, obviously I will go here, then I will come here, then I will come here, and so on. But I may have it in such a way that this one points here, the next I will get the next one here. So I will access this block, then from this block I will access this block, then I will again re-access the original old block. So in order to prevent this to a large extent, we organize it in the form of what are called buckets. So we will have algebra, biology, chemistry, and these will not directly point to the data records. These are my data records organized in a sequential fashion. I will not have the secondary key next pointers. This will point to a block which has got only pointers and next like this. This will point to the corresponding record. This will be the next one, this will be the third one, this will be the fourth one, this will be the fifth one. Biology will similarly point to a bucket. This will point to the first one, this will point to the second one, this will point to the third one, and so on. The advantage is that once I access this one, which may be a block or two blocks, then from here I will see which I need. I will see this one, and then if I want the third one, then I can store this. If I want to update all of them, then what I can do is I can update this one, then this one, and then move on to the next block. I can see all those which point to the same block, operate on them, and then go to somewhere else, a thing which I could not do before. So this way, if I do a bit of bucketing, then the secondary indexing will become better because the file is not organized sequentially according to the secondary index. So this has more advantages over maintaining the next pointer, because physically it will be either stored according to the primary index or the secondary index, only according to the primary index. So this bucketing helps us to reduce our time more. We will see next how to dynamically have, we can have multi-level secondary indexing also. We will next see, we will have levels of indexing, one level higher, one level higher. We will next see in B plus trees how this indexing can be maintained dynamically, and the load distribution of the files is done in a more equivalent fashion.